All right, chemists, you've done well. We've got two more left to go for the entire course, really. So let's get into this one now. Today we're going to talk about mass spectrometry. Now I'm going to fall all over that word, and it'll probably be just as bad in the next one. So hang in there. Um, Basically, when we're talking about mass spectrometry, we're talking about yet another analytical technique. Again, with our forensics unit, that's kind of the point. And this one can identify either elements or compounds, and it's the compounds part which is the most interesting part, by the concentration, and their concentration, sorry, by their mass to charge ratio. This means nothing to you yet, but it will. So let's look what it's made of. This is your sample tube here. You have an evacuated ionization chamber. Now, evacuated ionization, that means it's a vacuum in there. And you have a cathode filament just here connected to a high voltage source. So this means it's got an electric field with high voltages. So there's an electric field in there with high voltages that will accelerate the ions. We'll get into how it all works in a second, but this makes the ions. You have the high voltage field, and then it accelerates the ions from a repeller cathode, which is just here, because we're just making positive ions. So use the cathode here to repel it. So they'll push them towards these accelerating slits. Now the accelerating slits are there, and they make a very narrow beam as you go through, and you have a magnetic field whether it's somewhere between 500 to 8,000 Gauss, and this is used, that doesn't matter, it's just a strong field. This is used to deflect the beams to the detector. And it's got an ion collector, so the detector is usually a piece of metal that will create a circuit every time an ion hits it. Alright, so how does it work? Back to this, we're going to keep referring to this picture. You should be able to reproduce this picture. So, know this picture, know how to remake it, know how to draw it. That's why we've gone for the simple one. First step is ionization and acceleration. So you've got your gas or a vapor of your organic molecule. It's not always an organic molecule, but in forensics, it usually is an organic molecule. And it is added, in fact, it can be done with nearly anything. It is added, here is our black dots, and it is then either pushed in, so if it's a non-volatile one, you can just put it in directly. Otherwise, you slowly leak it in, and this is the one here. So if it's pushed in, so if it's a solid or a liquid that's not volatile, you just put it in there, and it'll vaporize because it is a vacuum in there. So it will start to vaporize, and then it goes past. It will run into this. There we go. So once it's inside, the filaments are bombarded. Sorry, the molecules are bombarded by. I don't know what I'll use. If I get a chance to use this stupid thing, the filaments are bombarded by the filament here. So the molecules are bombarded by the filament, and this ionizes them. And it ionizes molecules to make positive molecules. Now we'll get into that in a minute. So that's why it's actually really interesting, is it can be used for molecules. So you get positively charged radicals or molecular ions. Now, it becomes the parent ion. So for example, if we're talking about something like vinyl chloride is very unstable, so it will break into smaller ions. Carbon dioxide, a bit less so will still be some breakage, but we'll see what that means in a minute. So the positive ions are repelled by the cathode over here. They are pushed through, so they accelerate towards the anodes, which then puts them through this slit. So it goes through the slit, and as it's pulling towards them, they repel past. And then it turns into a fine beam. That's what this word collimates means. You need to know that word. Collimates means that you go from a mess into a fine beam. The low pressure is why we don't get much in the way of collisions between the air molecules, once in here, and the positive ions. Alright, so that's there. That's it through to this point here. So now we'll look at deflection and detection. So it enters a circular tube with a magnetic field, which again acts perpendicularly, and this causes the ions to deflect in a circular path. Now, there's fixed voltage and magnetic strength. So the radius of the path, we can kind of, it depends on the mass to charge ratio. If the ions are too heavy, they will go straight forward. If they're too light, so we have mass to charge, so if the charge is there and the mass is too high, they'll just go straight through and hit the wall. If they're too light, they will bend too far using the magnetic field. It's quite a delicate balancing act. But the ions with the mass to charge ratio usually of 1 to 1 or plus 1 makes it in here. They'll hit the detector. There's a nice focused beam. So, yep, too heavy, they'll think, too small, they'll hit the bottom of the tube. And this allows us to detect a single ion. Now, when we say single ion, we talked about how it could parent. We're talking about it allows us to measure a single parent ion. So when it hits the plate down here, that neutralizes the ions, which produces a voltage in a circuit, and then we record it on our computer. And this gives us our mass spectrum. Okay, so we assume that the charge of the ions is +1, and because it's only been hit by one electron, and then the voltage and the magnetic field strength, voltage, and the radius of the field. These are things we know, the radius of the circle, so we can calculate the mass of the ion. And the results of an MS are displayed as a mass spectrum. And here is our little example just here. So the x-axis is the mass to charge ratio. Because the charge is +1, it's simply molecular mass. So that's nice and handy. So here you've got 44, 28, 16. The y-axis is how strong the intensity is. Now, it's an arbitrary number, okay? So it always goes up from 0 to 100. So you can look at it as, 0 to 100, don't worry about that. So it doesn't matter what the top number is, it's always going to be 100. And the more of the ion that hits the detector, the higher this number is. So over here, the ion with the mass of 44, that was the most common one, so that's the one that we counted as hitting the detector. The ion with a mass of 16 and 28, they were the least common ones, but it doesn't matter, it's the most common one that makes a difference, and that's why that's at 100. And over here, this is what we've got. This is our molecular ion, and it's going to fracture just a little bit. It's going to fracture to give you this ion here and this ion here. But what we can see is that mostly we get this one, and we get a couple of those ones. So there's our 44, that's carbon dioxide. There is carbon, I guess it's carbon monoxide, and here is an oxygen. All right. So we can use it to identify both compounds and the isotopes of an element, which we'll have a look at in a second. So where can we use this in forensics? It's basically, we can use it to fingerprints of compounds. So we'll know even the ratio of things which are in that compound. We'll get more into that in a minute. And if we can compare this to databases of the mass spectrum of known compounds. We can use it with gas liquid chromatography, and this is where we get GCMS. And you can use this to analyze organic compounds. For example, if we wanted to work out where an oil spill came from, or oils, or paint thinners, or anything like that, anything organic, this is the aspect. This is what we would use to do it. So we'd use gas chromatography and mass. Actually, GC is gas, liquid, or high performance liquid chromatography. It's either of those. It's just chromatography and mass spectrometry. There are limitations, however. The sample must be a gas or a vapor. So you can use solids, but you've got to heat them slowly. But it's destructive. Again, it's another destructive one. Complex compounds will also have very complex mass spectra, spectra being the plural. So the mixture of compounds is often too hard to be individually identified, which means we do it in conjunction with HPLC or GLC. The reason we do it in conjunction is that allows us to separate it out into our various samples. The results are also much more accurate, and because the results are going to be much more accurate if we do combine these, because there are several compounds that can have the same retention time in chromatography. All right, so we're going to look at 3 examples now. First, we're going to look at carbon dioxide. This is our first one. So we bombard the electrons. It loses an electron to form a molecular ion. It's very unstable and will decompose, but because it's only got 3, there's only 3 possible arrangements. And in this case here, the parent ion is relatively stable compared to other ones, and it is the most abundant ion. But the important bit here, you can see the 44 line corresponds with the parent ion, 28 with the carbon monoxide ion, and the oxygen ion over here at 16. We can look at a much more complex one. Because it's larger, we can see that there's a lot more different ions that can happen. And because of this, the parent ion is not actually the most abundant of the lot. You may have noticed, though, that the parent ion is the largest line. Shortest line, largest mass. We can also look at isotopes. For example, over here we've got bromine gas. Now, we've got bromine gas at 3 different masses. So bromine is Br2, 3 different masses. And this is because there are isotopes of 79 and 81. And we can also work out the ratios. For here, we've got 2 bromine 160s, 2 bromine 158, 162. Okay? So yeah. So we can also work out the relevant abundancy of each one. And yeah, that's that. So hope that made sense. Hope you enjoyed it. And I'll see you in class.